Welcome to our introduction to stoichiometry, and this is chapter 12 in your textbook, so that's going to be the magic number to remember. And we spent a lot of time on balancing chemical equations, and in order to do stoichiometry, which is essentially learning how to work with quantities in chemistry and predict how many grams of reactants and products are needed in a chemical reaction, we always need to have a balanced chemical equation. What do the coefficients in the balanced chemical equation mean? We could read this equation in two ways. We could interpret this equation as saying 2 molecules of hydrogen sulfide plus 3 molecules of oxygen yield 2 molecules of sulfur dioxide plus 2 molecules of water. Or we could interpret the coefficients as meaning moles. And we could say 2 moles of hydrogen sulfide plus 3 moles of oxygen yields 2 moles of sulfur dioxide plus 2 moles of water. Most of the time we're going to be interpreting these coefficients as moles. So we could rewrite this as 2 moles of H2S plus 3 moles of O2 yields 2 moles of SO2 plus 2 moles of water. What happens if I convert moles to grams? We're hearkening back to chapter 10. We're doing a mole to mass conversion here. So I would have 2 moles of H2S times 34.1 grams in a mole of H2S plus 3 moles of oxygen times 32.0 grams in 1 mole of oxygen. Remember, oxygen is diatomic here, so our molar mass is 16 times 2. This yields 2 moles of sulfur dioxide. The molar mass of sulfur dioxide is 64.1 grams in a mole, plus 2 moles of water, and the molar mass of water is 18.0 grams in a mole. So we end up with 68.2 grams of hydrogen sulfide plus 96 grams of oxygen, and that yields 128.2 grams of sulfur dioxide plus 36.0 grams of water. When I add my reactants together, I get 164.2 grams, and when I add my products together, I get 164.2 grams. So we can prove that our reaction follows the law of conservation of mass. So we've converted moles into grams here for all of our reactants and products. So keep in mind as we work through the chapter that we always need to have a balanced chemical equation. Those coefficients are going to be very important to us, and for the most part they are going to represent moles of a substance. Now, let's start with the reaction nitrogen plus hydrogen makes ammonia, which has the formula NH3. The most important interpretation of this equation is that 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. Based on this interpretation, we can write ratios that relate the number of moles of reactants to the number of moles of products. And these ratios are called mole ratios. Okay, so the mole ratio is a conversion factor actually. And it's derived from the coefficients of the balanced chemical equation. So I want you to put this in your notes. So I can write several mole ratios from this balanced chemical equation. Here I can see that I have 1 mole of nitrogen for every 3 moles of hydrogen. That is 1 mole ratio. Or I have 2 moles of ammonia for every 1 mole of nitrogen. Or I could say that I have 3 moles of hydrogen for every 2 moles of ammonia. These are all 3 mole ratios that are derived from the balanced chemical equation. These are going to be very important in solving our stoichiometry problems. The mole ratio, just like the mole is the center of the chemistry universe, the mole ratio is the center of the stoichiometry universe. Woohoo! So the mole ratio is the center of the stoic universe. So it all comes down to writing the proper mole ratio. So how do we do that? Well, let's open up a new page here. All right, so now we're back in business. Let's go back with our original equation. And now we're going to use it to solve a problem. Okay, so our problem is going to be, I want the number of moles of ammonia produced. So I should say I want to find the number of moles of ammonia produced when 0.060 moles of nitrogen react. So how am I going to do this? The first thing I do is I find my given quantity. 0.60 moles of nitrogen is my given quantity, and I write that down. The next thing I do is I need to come up with a conversion factor. And my conversion factor, what it's going to do here is tell me how many, or help me find out how many moles of ammonia are produced. So if I want to find moles of ammonia goes on the top of the conversion factor. This is nothing new. So what we want, okay, so the units we need go on the top of the conversion factor. This should sound familiar. While the units we want to cancel out go on the bottom of the conversion factor. So I want moles of ammonia. I want to cancel out moles of nitrogen. That's what I started with. So that's what gets canceled out. Now, what are the numbers that go in my conversion factor? These numbers are the coefficients in the balanced chemical equation. So ammonia, there are 2 moles of ammonia in my balanced chemical equation. So that goes in my conversion factor in the numerator. And there's 1 mole of nitrogen in my balanced chemical equation. So that goes in my denominator. So remember that these numbers, they come from the balanced chemical equation. That's what they're coming from. That's why having that balanced chemical equation is so important. So I have my problem set up. So all I need to do now is do the simple math. And this is 0.60 times 2, which is 1.2 moles of ammonia. Let's say that in my problem, I want to make 5 moles of ammonia. Okay? How many moles of hydrogen do I need? So if I want to make 5 moles of ammonia, that's my given quantity. So I'll start out with 5 moles of ammonia. I want to find out moles of hydrogen, so that goes on the top of my conversion factor. Moles of ammonia needs to cancel, so it goes on the bottom. I look at my balanced chemical equation up here. I have 3 moles of hydrogen for for 2 moles of ammonia. So my ratio is 3 to 2. My problem is set up. So I have 5 times 3 divided by 2, which is 7.5 moles of hydrogen. Okay, let's say I wanted to find out how many moles of nitrogen that I would need, given the same circumstance. So again, I'm starting out with 5 moles of ammonia. How many moles of nitrogen do I need? That goes on the top of my conversion factor. Moles of ammonia goes on the bottom. I look up here, there's 1 mole of nitrogen for every 2 moles of ammonia. So my problem becomes 5 times 1 over 2, or 5 divided by 2, which is 2.5 moles of nitrogen. So what I've learned here is that in order to make 5 moles of ammonia, I need 7.5 moles of hydrogen and 2.5 moles of nitrogen. Basically what I've done here is altered this recipe. We think of a chemical reaction as a recipe. Many of you who cook or make cookies or something, you know how you alter your recipe. You might double your recipe or triple your recipe or half your recipe to alter the number of cookies or the dozens of cookies that you want to make. This is the exact same thing. We're altering our chemical recipe to get a specified amount of product or to use a specified amount of reactant. So that is the gist of stoichiometry. However, now we need to start a new page. When we're working in the lab, usually we're measuring in grams because we're using those balances. So our stoichiometry problems are not just going to be working in moles, but we want to work in grams. So we're going to use this same reaction because we're familiar with it. But we're going to work with grams this time. Okay, so what we want to do is calculate the number of grams of ammonia produced. So we want to find the number of grams of ammonia produced by the reaction of 5.40 grams of hydrogen. So we're coming from 5.40 grams of hydrogen, okay, with an excess of nitrogen. So it's not telling us how much nitrogen we need. It just means an excess means we have more than we need. That really doesn't count into the problem solving here. This is all we need to have to solve the problem. So I'll start with my given quantity, 5.40 grams of hydrogen. Now I'm working in grams. So I'm starting with grams of hydrogen. Remember that moles are the center of the chemistry universe. So in order to solve any problem, I need to convert to moles of hydrogen. That's going to be my first step in the problem. Okay? But I want to find moles, or I want to find grams of ammonia. But before I can go to grams of ammonia, I need moles of ammonia. Once I'm in moles, I can convert to grams of ammonia. So these are the steps that I'm going to follow. This part here is crucial when I'm going from moles of hydrogen to moles of ammonia. Okay? This is where I'm using my mole ratio. The mole ratio allows us to convert from one substance to another. Okay? Not from one unit to another, but from one substance to another. In this case, from hydrogen to ammonia. So, my first step, I'm going from grams of hydrogen to moles of hydrogen. So 1 mole goes on the top because that's what I need. The molar mass of H2 is 2.0 grams. Now I'm in moles of hydrogen. I need to convert to moles of ammonia. This is my conversion factor, my mole ratio. I want moles of ammonia. Okay. What goes on the bottom here moles of hydrogen. And this really is moles of hydrogen here. So we can see this is going to cancel out with that. Where do I get the numbers in the mole ratio? From the coefficients in the balanced chemical equation. We always need the balanced chemical equation. We can't do stoichiometry without it. So I have 2 moles of ammonia for 3 moles of hydrogen. That is my mole ratio. So we'll just circle it. There's the mole ratio. Okay, I've converted now from hydrogen to ammonia. Now that I'm in moles of ammonia, I can go to grams of ammonia. So I have grams of ammonia now on the top of this conversion factor. I want moles of ammonia to cancel, so it goes on the bottom. There are 17.0 grams of ammonia in 1 mole. That is the molar mass of NH3. So my problem is now set up. I can double check and see that my units cancel. Moles of ammonia, they cancel. Moles of hydrogen, they cancel. Grams of hydrogen, they cancel. I'm left with grams of ammonia. I want to find grams of ammonia. My problem is set up properly. Then I can do the math. So I'm doing 5.40 divided by 2 times 2 divided by 3 times 17.0. And I get 31 grams of ammonia. Remember, our problem has to have the correct number of significant digits. Okay, and it doesn't. My bad. So this has, oh, I'm sorry. Yeah, this has 3 significant figures. So we had a 0 here. Now we have 3 significant figures here. 31.0 grams of ammonia. So this is how we set up stoichiometry problems. The mole map that you use to convert from grams to moles, or moles to grams, or even liters to moles and moles to liters is still going to be important in this chapter, because you can see here we've done a grams to mole conversion. Here in this step, here we've done a mole to gram conversion. Okay, so we will also do liter conversions as well. And that might happen in some of these problems. But the most important thing is using the mole ratio. So when you come into class for the next class, you should be familiar with how to set up a simple stoichiometry problem using the mole ratio from the balanced chemical equation. What I want you to do is work on this problem. If we're using this reaction, okay, I want you to solve the problem. How many moles of aluminum are needed to form 3.7 moles of aluminum oxide? So pause the video, work on it yourself, and then double check my work. Now you should have gotten, this is how you would have set up your problem. You have 3.7 moles of aluminum, that's our given quantity. You want to find, or aluminum oxide, I'm sorry. You want to find moles of aluminum. So that goes on the top of your conversion factor. There are 4 moles of aluminum for 2 moles of aluminum oxide. So we have 3.7 times 4 divided by 2 is 7.4 moles of aluminum. What if I now am working with grams? Okay, so we're going to do a problem with grams. So I want to say, how many grams of aluminum are needed, cool word there, needed to form 10.0 grams of aluminum oxide. Okay? So what I want you to do is pause the video, and then I want you to solve the problem. Okay, we're back. So this is how you should have set up the problem. You have 10.0 grams of aluminum oxide. You then need to convert to moles. So 1 mole of aluminum oxide over the molar mass of aluminum oxide, which is 102.0 grams, times. Then we're going from moles of aluminum oxide to moles of aluminum. This is where our mole ratio comes in. So I look at my balanced chemical equation up here, 4 moles of aluminum for every 2 moles of aluminum oxide. Then I convert back to grams of aluminum. This is my molar mass of grams of aluminum, 27.0 grams in 1 mole of aluminum. So I have 10 grams divided by 102 times 4 divided by 2 times 27 is 5.29 grams of aluminum. So what I've done is I've taken this general recipe here and I've said, oh, I want to make 10 grams of aluminum oxide. How much aluminum am I going to need? And I was able to figure that out. I was able to alter my recipe. So we have now done stoichiometry.